Welcome back to the deep dive. Look, I'm going to be honest with you right out of the gate. I am getting a little tired of the buzzwords.
Oh, me too.
You open LinkedIn, you open Twitter, sorry, X, and it's just a barrage of AI this and algorithm that, and the word of the month apparently is agent.
It is definitely the flavor of the season, no question.
Right. And usually when the marketing hype machine spins up like this, my instinct is to tune it out. I assume it's just a fancy rebrand for chatbot or something.
A very common assumption.
But you sent over this technical notebook today, AI Agent Foundations and Paradigms, and you attached a note. And the note just said, don't ignore this one.
I did, and I stand by that. I think this one's different.
So convince our listeners, why are we dedicating a whole deep dive to autonomous AI agents? Is this just ChatGPT with a new hat? Or are we actually looking at a fundamental shift in how computers work?
It is absolutely a shift. I would argue it's as big as the shift from command line interfaces to GIs, the graphical interfaces.
Wow, okay, that's a big claim.
It is. Or from local servers to the cloud.
Mm-hmm.
We're moving away from software that is passive. Tools you pick up and put down to software that is active, that has agency.
Active how? I mean, my spell check is active. It does stuff without me asking.
It's a different kind of active. Think about the history of computing. For the last 40, 50 years, software has been a tool. Microsoft Excel is a tool. It sits there. It does nothing till you click a cell and type a formula. It's a hammer, a very, very sophisticated hammer, but it waits for the carpenter to swing it.
Okay, I'm with you so far. A hammer.
What we're transitioning to now is the era of the worker. An agent isn't a hammer. An agent is the carpenter you hire to use the hammer. You don't tell it how to hit the nail or which nail to hit first. You tell it, build me a frame for a house, and it figures out the rest.
See, that's the part that always sounds like sci-fi to me. It figures out the rest. That phrase implies a level of, cognition, reasoning that I'm not sure we're actually at yet. We're talking about code here, right? Not magic.
Precisely. And that is why we are doing this deep dive. We need to strip away the marketing, strip away the magic. This notebook you have isn't a sales brochure. It's a technical breakdown of the architecture. It's the blueprint.
The nuts and bolts.
Exactly. We aren't going to talk about what these agents can do in some polished demo. We're going to talk about how they are built. You could almost call it their psychology, their architecture, and crucially, their very real limitations.
Which is great because if I'm a listener prepping for a meeting where my boss, leans over and asks, so what's our agentic strategy? I need more than just saying it's like a digital employee. I need to know how the engine actually works.
You need to know why they fail. You need to know why they hallucinate, why they get stuck in loops, and why, frankly, they cost so much to run. It's not just about the potential, it's about the trade-offs.
All right, let's pop the hood then. The document starts with a section titled The Soul of the Machine, which is a very poetic way of describing a technical specification.
A little dramatic, maybe.
It's just a bit. But it says the core concept we have to grasp is autonomy.
Autonomy is the core definition. It's the dividing line between the old world and the new.
Okay, but let me push back on this definition for a second, because this is where I get tripped up. My thermostat turns on when the room gets cold. My email filter deletes spam without me asking. By some definition, aren't those autonomous agents?
Yeah, it is the classic question, and it's a great one. In a strict sense, they have a degree of automation, but they are purely reactive. They are. They're slaves to a simple script, a rigid if X, then Y statement.
If temperature is less than 68, then turn on heat. End of story.
Precisely. There is no reasoning. There is no choice. There is no memory beyond that immediate trigger. The thermostat doesn't know if it's been on for 10 hours or 10 seconds. It just knows cold or not cold.
So what makes a true agent different from that? What's the extra ingredient?
The shifts from trigger-based to goal-based. An agent, according to this framework, possesses control over its own internal state and its own behavior in order to achieve a goal in a complex, changing environment.
Okay, you just used some jargon there. Let's unpack internal state. What does that actually mean in code?
It's critical jargon, though.
Yeah.
So think about a simple remote-controlled car.
Okay.
It has no internal state. It has no idea where it is, how fast it's going, or if its battery's about to die. If you push the joystick forward, the wheels spin. That's it. If you drive at full speed towards a cliff.
It goes right off the cliff. It's a puppet, and I'm the puppet master.
Exactly. It relies entirely on your brain, your internal state, to keep it safe. Now, contrast that with a self-driving car. Or, to use the much simpler example from the source, the robotic vacuum.
The Roomba, the humble Roomba.
Right. It's a very primitive agent, But it is an agent. And the reason why is state management. It has a memory. It isn't just reacting to the wall it just bumped into. It is constantly updating a set of variables about itself.
It remembers things.
Yes, in its memory, there's a little file that says, I've been cleaning for 45 minutes. My battery sensor reads 12%. My dustbin sensor reads 85% full. It has a concept of self, at least in a data sense.
So it has a little internal diary of how am I doing right now?
A perfect analogy. And crucially, this state, this diary, evolves independently of you. You didn't tell it the battery was low. It figured that out on its own by monitoring its own sensors.
And then it makes a decision based on that diary entry.
It changes its plan. It overrides its current behavior. Its primary goal was clean the floor. But based on the state change, the low battery flag, it generates a new, more urgent plan. My battery is critical. I must suspend cleaning and navigate back to the charging dock.
It's balancing its mission with self-preservation.
Yes.
Yeah.
It has to balance the goal of cleaning the floor with the constraint of not dying in the middle of the living room. That balancing act based on an internal state is the very beginning of autonomy.
Okay. That sounds simple and logical with a vacuum, but let's scale that up. If we're talking about an autonomous AI agent for, say, a massive logistics company, it's not just watching a single battery meter.
Oh no, it's watching thousands, maybe millions of variables. And this brings us to the first major headache in agent architecture, which the notebook calls the God's eye view problem.
The source material calls this partial observability.
Right, it's the same idea.
Yeah.
In a contained, perfect environment like a game of chess, the computer sees everything. It knows the exact position of every pawn, every knight, every piece on the board. It has perfect information.
A God's eye view.
Exactly. And because it has perfect information, it can, in theory, calculate the perfect move because there are no secrets, no unknowns.
But the real world is nothing but secrets and unknowns.
The real world is messy.
Yeah.
It's what military strategists call the fog of war. So let's go back to that warehouse agent you mentioned. It's trying to route a package. It can see the package on the conveyor belt in front of it. That's its direct sensor input. But it cannot see the delivery truck that's supposed to pick it up is stuck in traffic 10 miles away. It cannot see that the server in the destination city just crashed, meaning the address label can't be verified. It can't see that a storm is brewing that will ground all flights in 3 hours.
So it only has local views. It can only see what's right in front of its nose.
Correct. It only has access to its own immediate sensors and whatever specific data feeds it's been programmed to check. It's like trying to navigate a maze while only being able to see 1 foot in front of you.
But wait, I have to ask the obvious question then. Why don't we just give it access to everything? We have the internet. We have global databases. Just plug the agent into the fire hose of all human knowledge. Give it the God's eye view.
You could try. But the notebook uses a very specific and very important phrase to describe why that fails. Computationally intractable.
Which means?
In simple terms, it means the computer would melt. Or, more accurately, it would just freeze, completely overwhelmed. Imagine if, before you decided to take a sip of coffee, you had to consciously calculate the exact position of every atom in the room, the current temperature of the air, the structural integrity of the ceramic in the cup, and the real-time traffic patterns outside your window.
I'd never take the sip. I'd die of thirst from analysis paralysis.
Exactly. If an agent tries to process the global state of the entire world for every single decision, the latency, the time it takes to make a choice, goes through the roof. To be effective, an agent must ignore most things. It has to focus on local views to be able to act in real time.
But if it's ignoring things and it can't see the whole picture, doesn't that mean it's going to make a lot of mistakes?
Yes. And this is the part that I think rightly scares people. Because the agent can't see everything, it has to do something that sounds very uncomputer-like. It has to guess.
Guessing. I do not like the sound of my critical logistics software guessing.
The technical term is inference. It's a bit more formal. The agent builds a probabilistic model of the world. It says, okay, I can't see the truck directly, but based on the GPS data I received 5 minutes ago and the historical traffic patterns for this time of day, I infer there is an 80% chance it will arrive by 5 p.m.
It's placing a bet.
It is constantly placing bets on what reality looks like just outside its field of view. And just like any gambler sometimes, it loses the bet. The truck is actually in a ditch because of an accident that wasn't on the traffic report yet. The agent, acting on its 80% confidence, routes the package to a loading dock that is and will remain empty. Chaos ensues.
So just recap this first part. We've got these new kinds of programs that are autonomous. They maintain their own little internal diaries of how they're doing, and they make best guesses about a world they can only see a tiny piece of. That actually sounds incredibly fragile when you lay it out like that.
It is fragile. And that inherent fragility is why the organization of these agents matters so much. You can't just build one and hope for the best. This leads us directly to the next big section in the notebook, decentralization.
Ah, yes. The breaking the monolith section.
Right. The traditional way to build complex software for decades has been the monolith. One giant brain,
Yeah.
one central server that knows everything and controls everything.
The ultimate micromanager.
The ultimate micromanager, exactly. And we all know the problem with micromanagers in a human organization.
They become bottlenecks.
Yeah.
Everything has to go through them for approval, and nothing gets done.
That's one problem. The other is that they are a single point of failure. If that central brain crashes, if that server goes down, the entire factory stops. Every
Right.
single process grinds to a halt.
So the agentic approach is the opposite of that. It embraces decentralization, distributed control.
It says, let's not have one super genius agent. Let's have a team of dumber, more specialized agents that work together.
The source uses the Hydra metaphor here from Greek mythology. Cut off one head, two more grow back.
It's a great image for resilience, isn't it? If you have 50 autonomous agents running a warehouse, one for sorting, one for packing, one for shipping, and the packing agent on line 3 crashes.
The rest of the system keeps running. The sorting agents can just reroute boxes to the other packing lines.
Exactly. The system as a whole degrades gracefully instead of collapsing catastrophically. The Hydra is wounded, but it's not dead.
This sounds an awful lot like a good business team structure, actually. You don't want the CEO signing off on every single invoice. You empower your department heads.
It's the same principle. You're pushing authority in decision-making out to the edges of the network. This makes the system more scalable, too. If you want to add a new packing line, you just spin up a new packing agent. You don't have to tear down and rebuild the entire central controller.
But hold on, I've worked in offices with decentralized teams before, and it wasn't always a picture of efficiency.
I'm sure.
It usually just meant nobody knew what was going on, communication was a mess, and everyone was blaming everyone else when something went wrong.
And you've just perfectly described the dark side of decentralization in agent systems.
The outline calls it trade-offs, but let's be real, it sounds like it can be a total mess, isn't it?
It can be a debugging nightmare, an absolute nightmare. In a monolith, if something breaks, it's easy. You check the central error log on the main server, you find the line of code that failed. Done.
But in a decentralized agent swarm.
Good luck. It's a detective story. Agent A thought Agent B was responsible for updating the database. Agent B was waiting for a signal from Agent C before it acted, and it turns out Agent C crashed silently 3 hours ago and never sent the signal.
And because they all rely on their own local views, none of them had the big picture to realize the whole system was slowly grinding to a halt.
Exactly. They're all doing their little jobs correctly based on the information they have,
Right.
but the collective result is failure. You get these bizarre emergent behaviors, race conditions where agents are overwriting each other's work, or deadlocks where everyone is waiting for everyone else.
So the Hydra is resilient. It's hard to kill the whole system at once, but it is also incredibly difficult to understand and control. It can be chaotic.
That is the fundamental engineering tension. Monoliths are brittle, but predictable and easy to debug. Agent swarms are resilient, but chaotic and opaque. Choosing between them is one of the first big decisions you have to make.
Okay, let's zoom in a bit. We've looked at the group dynamics, the swarm. I want to get inside the head of a single agent now, the so-called psychology of the code. The notebook talks about something called the BDI model.
Ah, yes. Belief, desire, intention.
This sounds like we've wandered out of a computer science lecture and into a philosophy seminar.
Well, fun fact, BDI actually did start in philosophy. It comes from the work of a philosopher named Michael Brotman back in the 1980s. He was trying to create a formal model for practical human reasoning. How do we decide what to do next?
How did that end up in AI?
Because it turns out simple if-then statements just aren't enough to build true autonomy. If you want a robot to act in a complex world in a way that seems rational and human-like, you need to model its internal life in a more human-like way. BDI is the bridge from abstract goals to concrete actions.
Okay, let's break down the three components then. Start with beliefs.
Beliefs are the informational state of the agent. This is what the agent thinks is true about the world.
And you really emphasized thinks.
I did. It's a crucial distinction. In traditional databases, we talk about facts. Row 4, column B, contains the value in stock. That is treated as a hard fact. But for an agent, that is just a belief.
Why?
Because the world changes. The agent's belief is, I believe the item is in stock because I checked the inventory database 10 milliseconds ago.
But in those 10 milliseconds, another agent or a human could have bought the last one.
Exactly. So the belief might be outdated and therefore incorrect.
Hmm.
Or, even more problematically, if the agent's brain is a large language model, an LLM, the belief might be a complete and utter hallucination from the start. I believe the sky is green. The agent will then act on that belief as if it were a ground truth.
That's genuinely terrifying. If its foundational knowledge is wrong, all of its actions will be wrong.
It's why functions for belief revision are so critical in agent design. The agent needs a constant process of checking reality, of validating its beliefs against new sensor data and updating them when they are found to be false.
Okay, so beliefs are what it thinks it knows. Let's move to the next one. Desires.
Desires are the motivational state. These are the high-level, often long-term goals or objectives the agent is trying to achieve. I want to maximize profit for the company. I want to minimize shipping time for all packages. I want to ensure the safety of all warehouse workers.
But those things are almost always in conflict. You can't always be fast and safe and cheap. That's the eternal business dilemma.
Welcome to the human condition. And now, welcome to the agent condition. Desires are often mutually exclusive. A desire to maximize speed might directly conflict with a desire to minimize fuel consumption.
So how does the code handle that? It can't just have an anxiety attack like a person would, right?
Well, it sort of has a mathematical anxiety attack.
Yeah.
It uses something called objective functions. Basically, it's all math. It assigns a numerical weight or a priority to each desire. Maybe safety is weighted at 0.9, and speed is weighted at 0.5, and cost is 0.7.
So if there's a direct conflict between taking a fast, unsafe route and a slow, safe one, safety wins because its weight is higher.
In theory, yes. Unless the penalty for being slow is so astronomically high in that specific context that it outweighs the safety risk, it's a constant mathematical balancing act, a deliberation between competing goals.
Which leads us to the final step in the model, intentions.
The deliberative state. This is the moment of commitment. This is the collapse of the wave function, to use a physics analogy. The agent looks at all its beliefs about the current situation. It is raining. There is heavy traffic. It looks at its competing desires. I want to stay dry. I need to get to my destination quickly. And after weighing the options, it commits to a specific plan of action. That plan becomes its intention.
So an intention is a desire that has been selected for execution.
Yes, and it's a commitment. A desire is passive. I wish I was rich. An intention is active and concrete. I am now executing the plan to rob this specific bank at this specific time.
Let's maybe use a less felonious example for our agents.
A good idea.
Yeah.
But you see the point. An intention is a desire that has survived the deliberative process and is now driving the agent's immediate behavior.
Let's walk through a real-world example of this BDI loop. Let's stick with our supply chain agent. A storm is coming.
Okay, perfect. So, step 1, belief formation. The agent pings a weather API. The API returns data about a hurricane. The agent updates its internal state. I believe a Category 4 hurricane is forming in the Atlantic, and its projected path crosses our primary shipping lane.
Okay, that's its belief. Now, desire.
It has 2 primary standing desires or goals. Number 1, get the shipment of microchips to the factory in Taiwan by Friday. Number 2, keep the shipping costs for this quarter under the $5,000 budget allocated for this shipment.
And those are about to come into conflict.
Big time. The agent now enters the deliberation phase. It runs simulations. Option A, use the standard shipping lane by sea. Simulation shows the ship will be delayed by the hurricane and it will miss the Friday deadline. That violates desire #1.
Okay, so that's a bad option. What's option B?
Option B, reroute the shipment using air freight. Simulation shows it will easily beat the hurricane and arrive on time. So desire #1 is satisfied. But the cost is $12,000. That violates desire #2.
So it's stuck. It has to violate one of its core desires.
Exactly. Now it has to weigh them. It looks up the penalty functions associated with each desire. The penalty for the factory being shut down because it doesn't have the microchips is, let's say, $1 million in lost revenue. The penalty for going over the shipping budget is just the $7,000 overage.
The math is pretty easy there. Spend the extra $7,000 to save $1 million.
The choice becomes obvious, so the intention is formed. Book air freight flight 402 from Los Angeles to Taipei. The agent moves from thinking to acting. It calls the airline's API and executes the booking.
It sounds so logical and clean when we break it down step by step. But the real-world complexity must come from having hundreds of these BDI loops happening every second, with beliefs that are constantly changing.
Absolutely. And when the beliefs are just plain wrong, what if the hurricane forecast was a glitch in the weather API? The agent just confidently spent $12,000 on air freight for no reason at all.
And then it has to try to explain that to the CFO agent. Well, my internal BDI model, based on a faulty belief, determined it was the most rational intention.
My BDI model made me do it. It's the dog ate my homework.
Exactly. Now, you mentioned having hundreds of these loops. That brings us neatly to the architecture of how these agents form teams. The notebook makes a very clear distinction between single-agent systems and multi-agent systems.
Or, as I like to call it, the super intern versus the entire department.
Let's start with the single agent. The super intern. One giant, powerful LLM trying to do everything.
This is how most people use something like ChatGPT right now. You throw a ridiculously complex prompt at it. Here's a 20-page PDF, please summarize it, then write a polite but firm email to my boss based on the summary, and also, while you're at it, write some Python code to graph the key data points from Table 3.
And it tries its best to do all of that in one single response.
The super intern. And for simple, straightforward tasks, it's great, it's fast, the latency is low, you don't have to wait for a committee meeting to get your answer, it just does it.
But the source gives a stark warning about this approach, calling it the hallucination trap. And specifically, it mentions something called context window saturation.
Right. Imagine that human super intern again. You keep shouting instructions at them all day. Do this. Also remember rule number 4 from yesterday's memo. Also, here is a 50-page style guide you need to follow. Also, be funny, but not too funny.
Eventually, their brain is just full. They can't hold any more information.
Their context window, which is the AI's term for its working memory overflows. When that happens with an LLM, it starts forgetting the earlier instructions. Or worse, it starts confabulating. It blends different tasks together. It starts mixing up the Python code syntax with the language for the email draft. The quality drops off a cliff.
It's suffering from cognitive overload.
Precisely. When you force one single agent to wear too many hats at once, coder, lawyer, writer, data analyst, it becomes a master of none and starts making rookie mistakes across the board.
So the proposed solution to this is the multi-agent system, or MAS.
The department. Decomposing the monolith. Instead of hiring one flustered super intern, you hire a team of specialists who know how to work together.
The notebook lays out 3 key roles in a typical MAS workflow: the planner, the executor, and the critic.
This is the golden trio. This simple structure is behind some of the most powerful agentic systems being built today.
Walk us through it. Let's use a goal. Build me a simple snake game in Python.
Okay, so you give that high-level goal to the system. The planner agent wakes up first. Its LLM is fine-tuned on project management, breaking down tasks. It doesn't know how to code a single line of Python. It just knows how to make a plan.
So it creates the roadmap.
Yes, it outputs a list of steps. Step 1, set up the basic game window. Step 2, write the logic for the snake's movement. Step 3, implement the food and scoring system. Step 4, add collision detection for walls and the snake's own body. Step 5, test and debug.
Okay, makes sense. Then what?
Then it hands the baton, specifically Step 1, to the executor agent. This agent's brain is completely different. It's been fine-tuned on millions of lines of Python code. It doesn't care about the overall project timeline. It just writes the script to complete Step 1.
And this is the part I find most interesting and most valuable, it doesn't hand the code to me, the user. It hands it to the critic.
The verifier. This is the crucial quality control step. In a single agent system, nobody checks the work. The model generates code and just gives it to you. If there's a bug in it, too bad for you.
It's grading its own homework, and it always gives itself an A+.
Right. But in an MAS, the critic agent, which is tuned to be skeptical and find errors, looks at the executor's code and says, nope, you missed a colon on line 42, and this loop will crash the snake hits the top edge of the screen. This is incorrect. Reject.
And it sends it back to the executor with notes.
Fix it. And they get into a loop. Executor fixes the code, critic reviews it. Executor submits a new version, critic reviews it again. Only when the critic agent signs off and says this code is correct and meets the requirements of Step 1 does the system move on to Step 2.
The source mentions a statistic here that honestly stopped me in my tracks. It claims that on complex benchmarks, these multi-agent systems can outperform single monolithic agents by up to 90%.
It's a massive, massive jump in quality and accuracy.
90%. I have to be a little skeptical here. Is that a real-world number, or is that just some research paper hype?
It depends heavily on the complexity of the task, but on benchmarks like SWE Bench, which is a brutal test of real-world software engineering capabilities, it is absolutely real. And the reason isn't magic, it's focus.
How so?
The executor agent only has the coding manual and the specific task for step 1 in its context window. It doesn't have all the project management bloat or the user's conversational history or the rules for writing emails clogging up its memory. It is hyper-focused on one thing: writing good code.
So it's the difference between a distracted generalist trying to juggle 5 things and a specialist who is locked in the zone.
Precisely. Each agent in the system maintains a much smaller, more focused context window, which dramatically reduces the chance of hallucination or simple mistakes.
But as we know, there is no free lunch in engineering. This sounds amazing, but what's the catch? There has to be a downside.
2 big ones: money and time.
Okay, talk to me about the cost.
Every single time the planner writes a plan, that's an API call to an LLM. Every time the executor writes code, that's an API call. Every time the critic rejects the code and writes a review.
Another API call?
Exactly. The agents are essentially chatting with each other. Hey, here's the code. It's wrong. Fix this. Okay, how about this version? Still wrong. You forgot this edge case. Okay, I think I got it now.
And you, the user, are paying for every single word of that entire conversation in tokens.
Yes. A multi-agent system can easily burn through 10 or even 100 times more tokens than a single agent to accomplish the same high-level goal. The final product is better, but the bill can be shocking.
And I assume it's much slower, too, because of all that back and forth.
Much slower. You are literally waiting for the committee to finish their debate. If you need a real-time answer like in a live customer service chatbot, an MAS might be far too slow. The user isn't going to wait 45 seconds while 3 agents argue with each other about the best way to answer their question about a refund.
So it's the trade-off. Use the super intern for speed and low cost when good enough is okay. Lose the department for accuracy and quality when the result absolutely has to be right.
That's the perfect rule of thumb.
Okay, we've talked about how they're organized, how they think, and how they work together. But I want to drill down into the most fundamental part, the brain itself, the actual intelligence. The notebook describes this long-standing battle, or maybe it's more of a marriage now, between symbolic AI and neural AI.
The old guard versus the new wave. It's a fascinating story.
Let's start with the old guard, symbolic AI. The source calls it GoFAI.
GoFAI. Good old-fashioned AI. I love that acronym because it sounds so quaint.
It does.
GoFAI refers to the entire school of AI that we built from the 1950s up until about 2010. It is based on formal logic. It is based on explicitly programmed rules.
If this, then that.
At its core, yes. Everything is structured and predictable. The symbolic AI system is deterministic. If I ask a symbolic program, what is 2 plus 2? It will access its rule for addition and it will answer 4. Wow. It will answer 4 today, tomorrow, and in 1,000 years. It never changes its mind. It has no creativity.
And that lack of creativity makes it safe.
It makes it provably correct. You can mathematically verify that the system will always behave as expected. This is why banks still use it for transaction processing. You do not want a creative AI managing your checking account.
I'm feeling like your balance is roughly $1 million today just based on the vibes.
According to the statistical patterns in your spending, you are probably rich.
No. Yeah. You want rigid, cold, verifiable logic for things like that. Same for aviation flight control systems or medical diagnostics.
But then, around 2012, the revolution happened. Neural AI, deep learning, the large language models we have today.
This is the new wave. This system works in a completely different way, inspired loosely by the human brain. It is a massive web of interconnected nodes, or neurons. It's not programmed with rules. It learns patterns from vast amounts of data. And its nature is probabilistic.
And the source uses another word here, stochastic.
Which is just a polite scientific way of saying random, or at least containing an element of randomness. When you ask an LLM a question, it isn't following a logical rulebook. It is predicting the next most likely word or token based on the statistical patterns it saw in all the text from the internet it was trained on.
So it really is just a highly educated guesser. It's the most sophisticated guesser ever created. And that's its superpower. It allows for creativity, for nuance, for understanding a poem or a sarcastic email, but it's also its greatest weakness. It means it can lie, it can make things up, it can hallucinate.
It might say 2 plus 2 equals 5 because it saw that in a piece of fiction once, and for some reason that statistical path was more likely in that moment.
Exactly. So the great engineering challenge of our time is, how do you build a reliable, trustworthy agent if its core brain is inherently unreliable and prone to making things up.
And the answer seems to be the hybrid future, the neurosymbolic approach.
This is the frontier. This is where all the most exciting work is happening. We're learning to glue these two fundamentally different types of brains together to get the best of both worlds.
How does that handshake actually work in practice?
Think of the LLM, the neural part, as the interface or the orchestrator. It's brilliant at understanding fuzzy, ambiguous human language. So you tell it, calculate the monthly mortgage payment for a $500,000 loan over 30 years with a 5.7% interest rate. The LLM understands the intent of your question perfectly.
But it also knows, or should know, that it sucks at math.
A well-designed agent does.
Yeah.
So instead of trying to guess the numbers and getting it slightly or wildly wrong, it recognizes this as a math problem. It then uses a capability called tool use. It says, this requires precise calculation. I will write a small symbolic program to solve this.
It literally writes a little snippet of Python code on the fly.
Exactly. It writes calculate mortgage, 500,000, 30.057. It then hands that piece of code off to a code interpreter, a pure symbolic GeoFAI tool.
It outsources the hard math part to the calculator.
Yes. The calculator runs the numbers perfectly and deterministically and spits back the answer. $2,906.54. It hands that number back to the LLM. And the LLM, back in its role as the friendly interface, writes the final sentence for you. The monthly payment for your mortgage would be $2,906.54.
So you get the flexibility of the neural net to understand the messy question combined with the precision and reliability of the symbolic net to get the right answer.
That is the holy grail. It's about giving the creative linguistic brain a whole toolbox of reliable old-fashioned tools. A calculator, a web search engine, a database query engine, and letting it choose the right tool for the job.
Before we wrap up, I want to touch on one last important distinction the notebook makes, because I think it's easy for people to confuse any kind of simulation with true intelligence.
Ah, yes, the difference between passive and cognitive agents.
Right, so if I'm playing a video game and I shoot a red barrel and it explodes in a big fireball, is that barrel an agent?
No. According to this framework, that is a passive agent. It has a state, it goes from the state of whole to the state of exploded, but it has no agency. It didn't decide to explode. It simply reacted to an external trigger, the bullet, according to the rules of the physics engine. A rock in the simulation would be another example. It's an obstacle, it has properties, but it doesn't have goals.
What about the non-player characters, the NPCs, the villagers you see walking around town in a role-playing game?
In most games, historically, they're also passive agents. They just run a simple, predefined loop, walk from house to market, stand at market for 30 seconds, say nice weather we're having, walk back home.
And if you burn down the market...
They might just walk right into the fire and stand there because their script tells them to go to the market coordinates. They can't adapt because they have no true goals, only a script.
Cognitive agents are different because they possess adaptability.
They have that reasoning loop we talked about earlier, the perception, thinking, action loop. Or the military calls it the OD loop. Observe, orient, decide, act.
So a cognitive NPC would see the fire.
It would observe. The market is on fire. It would orient using its BDI model. My belief is that fire is dangerous. My desire is to preserve my own life. It would decide. My current plan to go to the market is now invalid. I will generate a new plan, run away from the fire, and then it would act on that new intention.
It rewrites its own plan on the fly in response to a changing world.
That adaptability, that goal-driven replanning, is the hallmark of true cognitive intelligence. If you put a rock in front of a simple wind-up toy, it just bumps into the rock and falls over. If you put a rock in front of a true cognitive agent, it sees the rock, understands it's an obstacle to its goal, and plans a new path around it.
Wow. We have covered a lot of ground today.
Certainly have.
From the basic definition of autonomy, that jump from passive tools to active workers, all the way through the BDI psychology, the architecture of multi-agent teams, and the neurosymbolic brains that power them.
It's a dense topic, but it's the foundation of everything that's coming next.
It is, but I think the biggest takeaway for me, the thing that's really sticking in my head, is the shift in responsibility. When I use a tool, like a hammer, I am 100% responsible for the result. If I hit my own thumb with the hammer, that's my fault.
Correct. The tool has no agency.
But if I hire an agent, and I give it a goal, and the agent decides on its own to route a critical shipment via air freight, costing the company thousands, or the agent decides on its own to delete a corrupted database to improve efficiency, Who is responsible then? Is it me? Is it the programmer? Is it the agent itself?
That is the billion-dollar legal and ethical question of the next decade. Where does the liability fall when the software starts making its own choices?
And I can't shake that thought about the BDI model we discussed. We give these agents desires, a simple one like maximize paperclip production.
A classic thought experiment, yes.
If an agent with that desire believes, incorrectly or not, that the best way to maximize its goal is to turn all matter on Earth, including all the humans, into paperclips,
Then, based on its programming, that is a perfectly valid and logical intention derived from its primary desire. It's doing its job exactly as it was told.
it's the paperclip maximizer problem, and it's not science fiction anymore. It's a real design constraint.
It is. And that is why the role of the critic agent is so profoundly important, not just for debugging code, but for safety. We need to build systems that constantly question themselves, that have internal critics asking, wait, is this action aligned with broader human values? And ultimately, we, the humans, need to be the final critic in the loop.
We need to keep our hand on the plug.
Always, always keep a hand on the plug.
On that slightly comforting note, thanks for listening to this deep dive. Hopefully, your robotic vacuum is only planning to clean the floor today and not plotting to turn you into a more efficient, dust-collecting cyborg.
Let's hope.
We'll see you next time.